Okay, continuing on in section 5.7, just want to show you a few more examples of solving inequalities. And just a reminder, the directions on these problems are to solve, write the answer using interval notation, and also to illustrate with a graph. So we'll start off with a solving process, which is very similar to solving a linear equation. So our goal is to try and get this x by itself, and we're going to take steps to try and make that happen. The first thing I'd want to do here is move this plus 7 to the other side. I would do that by subtracting 7 on both sides. That would cause that to cancel over here, and I would have 4x is less than 8. And then I'm trying to get that x by itself now, and it's connected to the 4 by multiplication, so I would divide both sides by 4, which would cause that 4 to cancel. And we saw that sometimes you have to switch this inequality, but that's only if you divide by a negative. We're dividing by positive 4 here, so we don't have to make a switch on that. So it'll just be an x on the left, it'll still be a less than, and 8 divided by 4 is 2. So there's one part of our answer. There's the solution expressed as an inequality. Then they want us to write it using interval notation and also to do a graph. I actually find it a little easier to do the graph first and then write the interval notation from that, and the order doesn't really matter. I would just take whatever number came up here and put that in the middle of my graph. Because it says x is strictly less than 2, I would do an open circle to show that the 2 is not included. And when your x is on the left side, the arrow points the way you want to go. Our x's are to the left of or smaller than 2. So that would be like this. And then the interval notation would be that this goes forever to the left, which is negative infinity. And on the right hand side it stops at 2, but 2 is not included, so I would use rounded parentheses to illustrate that. Alright, so there's our solution as an inequality, there's the graph, and interval notation. Let's try another one. 5k minus 1 is less than or equal to 2k plus 8. I would want to get the values of the variable on one side, the numbers on the other, so I'll move the values of k to the left. So my first step would be to subtract 2k from both sides. Those cancel. I get 3k minus 1 is less than or equal to 8. I would add 1 to both sides to move the numbers to the right since I kept the variable on the left. And I get 3k is less than or equal to 9. 3 is connected by multiplication. Get rid of it by division. And it looks like k would be less than or equal to 3. And then the graph of that, I would do my number line, I would put 3 in the middle. You could start with an open circle if you want, but because this says or equal to, we're going to close that circle in. That's the way we show that the 3 is included as part of our solution. The arrow, when k is on the left, will point in the direction we should draw our graph. The values of k we want are the ones that are smaller than or to the left of 3. So I start at that 3 which is included, draw an arrow to the left illustrating my solutions. So there's the solve, there's the graph. The interval notation always goes from left to right. On the left hand side our boundary is negative infinity. We always put rounded on infinities because we can't ever reach them, so they're always listed as not included. On our right the graph ends at 3 and the 3 is included, and we illustrate that by using the squared off bracket instead of using the parentheses that are rounded. So solution, graph, and solution in interval notation. Alright, let's go ahead and look at one more on this page. This one just has a little bit more simplification to do. When we have parentheses, I would start off by using the distributive property to clear those. So distribute the 4, 12x, and 4 times negative 5 would be minus 20. And that's greater than distribute the 5. 5 times 2x is 10x. And 5 times negative 3 is negative 15. And then I'd want to move the x's to the left and the constant terms to the right. So subtract 10x from both sides to get rid of this one on the left and move it, on the right, move it over to the left. I like to sometimes at the same time move my constant term over, so if I add 20 here that would cause that to cancel. 20 on the other side keeps things balanced. Over here 12x minus 10x would be bigger number's positive. So positive 2x is greater than negative 15 plus 20 would be 5. And then divide both sides by 2 to get rid of this 2. and it looks like the solution would be that x is greater than 5/2. And normally when I go to graph something like 5/2, I might think of it as a mixed number and say 2 goes into 5 twice with 1 left over, so this is 2.5. And that would tell me, okay, I need to plot that halfway between 2 and 3. But really when you're doing inequalities, we typically just put one number on there, which is this number. We indicate whether it's included or not. This one's not included, so I would do an open circle. The arrow points the way. If x is greater than 5/2, then x is to the right of 5/2, so my graph would go like this. When I go to do the interval notation for that, the left-hand boundary is 5/2, which is not included because of the open circle and then no equal portion line there. And then on the right, we go forever or to infinity, which can never be included, so that would be rounded. So solve, graph, interval notation. Those are the three ways that we would express those. Alright, let me show you one more example of solving an inequality. And again, our directions would be to solve, graph, and write the answer in interval notation. And when I look at this one, the first thing I notice is that it has fractions. And just like we can solve an equation with fractions by multiplying through by the LCD, we can do the same thing if it's an inequality. So the least common denominator of 3, 6, and 2 would be 6. That's divisible. All three of these go into 6 evenly. So I would take each term and I would multiply that by 6. So 6 times 5/3 minus 6 times 1/6 x, and that would still be less than 6 times 1/2. It would still be less than because as long as we're not multiplying by a negative, the inequality continues to point in the same direction. And then just showing the canceling here, and this is the reason we multiplied by the 6, is it should make all the fractions go away. This denominator of 3 goes into this 6 twice. This denominator of 6 cancels that 6. This denominator of 2 goes into that 6 3 times. So if we look at what's left over, in the first term we have 2 times 5, so that's 10. Here the 6's are gone, so we just have minus 1x, or just minus x. And on the other side we have less than 3 from the 3 times 1. And then we could subtract 10 from both sides. Those cancel. At that point it looks like I'm done almost. Negative x is less than, let's see, 3 minus 10 would be negative 7. But we don't want x by itself, or negative x by itself. We want x by itself. So I still have to get rid of that negative, and I would do that by dividing by negative 1. But if I divide by negative, I have to flip the direction on that inequality, or reverse the direction on that inequality. So that's going to become a greater than at the moment I divide by negative 1. And so the two negatives here cancel, and I get positive x is greater than negative 7 over negative 1, which would be positive 7. And then for the graph portion there, I would put the 7. There's no or equal, so an open circle. X is greater than or to the right of 7. And that would be my graph. Interval notation, left-hand side of the boundary is 7, which is not included. And it goes forever to the right, or to infinity, which is never included. So there's my solution, my graph, and the interval notation. And again, the key step here that makes this an easier problem is to notice the fractions at the beginning, figure out their least common denominator, and multiply every single term by that. That should eliminate all your fractions and make the rest of the work go smoother. So as we go through and we solved all these examples of inequalities, we should notice it's just like solving an equation. There's really just one difference in the solving process, which we saw right here. If at any point along the way you divide by a negative, then you're going to reverse the direction of the inequality. That would also be true for multiplying by a negative, but that's actually very rare. So it usually is a division step, and it's usually the last step. So you're trying to get x by itself, you divide by its coefficient. Sometimes that coefficient is negative. If that's the case, you have to reverse the direction. So that's the key thing to remember about solving linear inequalities, is if we multiply or divide both sides of an inequality by a negative, then we must reverse the direction of that inequality. And except for that step, it doesn't feel much different to solve an inequality versus an equation. There are the extra steps, though, of doing the graph and the interval notation that tend to go with these. So a lot of times we have 3 parts to our answer. But as far as the algebra goes, this is the only step that feels different. Alright, let me go ahead and show you another type of inequality called a compound inequality, or sometimes I'll refer to it as a three-part inequality, where instead of just a left and a right-hand side, we have a left side, a right side, and also a middle. And when we're trying to solve this type of inequality, our goal is generally to try and get that x by itself in the middle. And so you kind of focus just on that middle piece, 3x plus 1, and you think, if I wanted that x by itself, I'd have to get rid of that 3 and I'd have to get rid of that 1. Following the normal order that we do with equations, I would try and get rid of that plus 1 first, and I would do a minus 1 to get rid of a plus 1, and those would cancel. When we're doing an equation or a standard inequality, we say if you're going to subtract 1 from one side, you have to subtract it from the other as well. When you're doing a three-part inequality, if you subtract 1 from one part, you have to subtract 1 from all three parts to keep that balanced. So we do negative 5 minus 1 is negative 6. There the ones canceled, so we have less than or equal to 3x, and less than or equal to right here from there, and then 13 minus 1 would be 12. We're closer to our goal, but we're not there yet. We want x to be by itself in the middle, and we still have that 3 in front of the x. It's connected by multiplication, so I'd get rid of it by division. And again, with three-part inequalities or compound inequalities, if you're going to divide one part, you divide all parts. So I'm dividing the middle by 3 because that cancels that and leaves the x alone. I'm dividing the outsides by 3 to make sure I keep balance. And then just looking at where that would take me, on the left I have negative 2. That's less than or equal to x, which is less than or equal to 12 over 3, which would be 4. And then that's the solution. Once you get that x by itself, we'd say you've solved it. The graph part, I would put both of those numbers, the negative 2 and the 4. I would think about whether they're included or not. They both have the or equals, so they both get solid circles. And then where's the x? The x is in between negative 2 and 4, and so our solution graph is that portion of the number line that is between negative 2 and 4, and including negative 2 and 4 because the extra lines. And then for interval notation, where's our graph start on the left? Negative 2, which is included, so square bracket. And on the right, it ends at 4, which is also included, so another square bracket. So that's how you would solve a three-part inequality. Your goal is to get the x by itself in the middle. You think about it the same way. If you want to get rid of a plus 1, subtract 1, but do it from all three parts. You want to get rid of that 3 times in front of the x, divide by 3, but do that on all three parts. And then typically when you go to graph one of these, since the x is in between those values, your graph will be drawn in between those values. Let's take a look at one more, just to get some extra practice with that. So again, it's a three-part inequality. We have 7 on the left, 5 minus 2x in the middle, and 13 on the right. Our goal is to get that x by itself. I have to get rid of the 5 and the negative 2. We usually try and get rid of the terms, the constant terms first. So I'd subtract 5 to cancel those, but I have to do that on the right and the left as well. On the left, 7 minus 5 is 2. We had our 5's cancel in the middle. The less than copies down, and I have negative 2x. The less than or equal to copies down, and 13 minus 5 would be 8. So I'm almost there. I just want to get this x by itself. There's a negative 2 that's multiplying that, so the opposite of that would be to divide by negative 2. If I do that in the middle, I have to do it to all three parts. I'm doing it in the middle to make those cancel. But we still have to remember that when you're working with an inequality, whether it's the simpler type or this compound three-part type, if you divide by a negative, you have to reverse the direction of your inequality. So this less than switches to be a greater than. That less than or equal switches to be a greater than or equal. And so when I look at where that puts me, 2 over negative 2 is negative 1. This is now a greater than. The x is now by itself. This is now a greater than or equal, and 8 over negative 2 is negative 4. One thing that should always be true with the three-part inequality is that two inequalities, if you think of them as arrows, should point in the same direction, and they should point to the smaller number. And negative 4 is smaller than negative 1, because if you think of that on the number line, negative 4 would be to the left of negative 1. And when I go to graph this, I would actually like to see the numbers in the same order here as they are there. So when I divide by negative and get these pointed to the right, I usually want to go ahead and flip everything around and put the -4 and the x and the -1 and just take these symbols with it. That was in between the x and the -4, and it was pointing at the -4, so it still points at the -4. That symbol was between the -1 and the x, and it was pointed at the x, so it would still point at the x. So you could do your graph from here, but personally I always like this to go from small to large because that's the way my graph is going to look, and that's the way my interval notation is going to be written out. So I find it smoother if I do it that way. And then I can say the -4 is included, solid circle, and the -1 is not included, so open circle, and x is in between those two, so the graph goes in between those two. And for interval notation, the left boundary is -4, which is included. The right boundary is -1, which is not included. And that would be my solve, graph, and interval notation. I would argue this is a correct solution too, but I just prefer it to be smallest number on the left, bigger number on the right, so I just kind of reverse that whole thing at the very end. Okay.